And hi, everybody. I realize I put this out sort of late, but here is the second lecture on glaciers. And the first part of this lecture will focus on glacial movement. So in the previous lecture, number 10, we covered the definition of what a glacier is, how glaciers fit into the water cycle, and how glaciers accumulate and ablate, as well as different physical forms of glaciers and what happens to glaciers when they reach the ocean, as well as information about sea ice and other types of ice found around Antarctica. And today's lecture is going to focus on how glaciers move during the first half, and then the second half of this lecture will talk about how glaciers erode or break up the rock underneath them. And so congratulations on getting through the exam. We are now in the second half of the course, and the material that we're covering now will be on the final. And as for the material covered in the first 5 weeks, aka the material that you had on the midterm, continue to review your notes because the final exam will be somewhat cumulative, and there will be some questions. The questions will mostly be focused on the material from weeks 6 through 9, like this week onward. But there will be material. But there's going to be questions about the earlier stuff also. So continue to review your notes and the study guide for the midterm and keep those on hand. Reminder that there is a lab on fossils due this Friday, February 12th, and that the first reading assignment is due on Sunday, February 14th. I'd also like to mention that there's a colloquium happening this week for those of you who might have seen the periodic table and wondered why most scientists and most disciplines of science don't talk about a lot of the heavier elements. A lot of it's because they're not very common, but it turns out that geologists are actually often interested in them because they do occur in tiny amounts in minerals, kind of like how some minerals incorporate bits of uranium, and that's used to measure how old the rocks are. But the rare earth elements, which are some of the elements that are in the blocks below the main table, are actually really heavily studied by geologists because they form some interesting patterns, and there's a lot of current interest in geochemistry about what those patterns say about geologic processes. So we have a visiting professor coming tomorrow at 2 o'clock, and the Zoom link is in this diagram here, who will talk about how you can study rare earth elements to possibly gain insight into ancient life. So that is actually a visiting professor from South Africa, which is one side benefit of one sort of side benefit of having to do everything virtually. They've been able to get some international researchers who otherwise would not have made it over here to talk about their work. And also, I wanted to mention that Monday is a holiday. Monday, UCSB observes the President's Day holiday. And so on February 15th, I will not be recording a lecture, and I will not be holding office hours that day. On Wednesday, February 17th, we're going to move into the first of 3 lectures about the human history of Antarctica, and there will be a review session covering the material from this week, aka lectures 10 and 11, at the start of office hours that day. So February 17th is the next review session we're going to have. So Lecture 11A, the video you're watching now, first introduces another category of glacier, and that is the distinction between warm and cold-based glaciers and what that actually means for Antarctic glaciers. And then we go into some information about glacial movement, because glaciers have several different mechanisms for moving, and they respond to stress in several different ways, depending on a variety of factors. Then Lecture 11B will focus on what happens to the rocks that the glacier is traveling over. Because it turns out in a nonpolar environment, what actually breaks the rock down and sculpts the land into mountains and valleys is liquid water. In Antarctica, there is very little liquid water. Most of the water is frozen. And so the biggest driver of erosion and the biggest shaper of the land, essentially, are glaciers. And we'll talk about the consequences of that a little bit. So, oops. I apologize for that. Now, in the previous lecture, we went over a number of types of glaciers that were defined by their shape. We have continental glaciers like ice caps and ice sheets, which are defined um, by the fact that they are not constrained by their surrounding topography. They flow over everything. And then there's the various cirque glaciers and alpine glaciers and valley glaciers and tidewater glaciers and such that are defined by what they flow through or where they end up in the case of tidewater glaciers. There is a completely separate category of glacier, it turns out, that we have to consider. And this has a lot to do with temperature. Some glaciers are considered to be cold-based, and some are considered to be warm-based. And an important term for me to introduce here is the pressure melting temperature. Several times in this course, I've mentioned the fact that the temperature at which liquid water freezes to ice and vice versa is going to be dependent on pressure. And that comes into play here because the pressure melting temperature is going to drop, which means that liquid water can exist at lower and lower temperatures as you go from the top of the glacier to the bottom of the glacier. And that's because the pressure is increasing. The pressure is increasing from the top of the glacier to the bottom of the glacier because the bottom of the glacier is under higher pressure from the weight of all the overlying ice. And so this is where the latitude of the glacier comes into play, because we have glaciers in the polar regions, like Antarctica and Greenland, and we also have glaciers in alpine areas of lower latitudes, such as the glaciers in the Himalaya, or those in the Andes Mountains, or those that gave the name to Glacier National Park in Montana. Now, in the polar regions, the sunlight is pretty weak. Remember that in Antarctica and Greenland, we're at a high latitude, and the sunlight is meeting the Earth at an angle, and it's very spread out. So it doesn't do a very good job of heating the surface of the glacier, even in the summer. And so in polar glaciers or cold-based glaciers, you actually have the ice temperature goes from cooler at the top to slightly warmer at the bottom because the bottom is warmed somewhat by friction and from geothermal heat, the heat from the Earth's surface itself. The heat from the Earth actually does a more effective job of heating the glacier than the sun does in polar areas. Now, notice that in the diagram on the left, there's a line representing the pressure melt temperature at different depths, because different depths correspond with different pressures. And notice how the ice temperature doesn't intersect with that at all. And that means that the glacier is not going to experience very much melting at any depth. It is considered to be cold-based because even though the bottom is warmer than the top, it's much colder than the pressure melting temperature. Now, glaciers in more tropical or temperate latitudes will experience stronger sunlight, and they will thus be warmer overall, and especially so at the surface. And so the ice will actually be warmest at the surface and get colder as you go down and are thus farther from the sun. Now, the average ice temperature of a warm-based glacier as you move down the ice just about follows the pressure melting temperature. This means that while you have ice, you can also have liquid water forming in considerable amounts. And this means that warm-based or temperate glaciers tend to produce a lot of meltwater, and they have quite a bit of liquid water lubricating them as they move over the land. This is something we don't really see much of in Antarctica. And as it turns out, this will have consequences for how glaciers move because warm-based glaciers will tend to move a lot more by basal sliding when they simply kind of move forward as a single mass. They'll experience that a lot more than the cold-based glaciers will, and it's because they're more lubricated by the meltwater. Now, remember that on land, a glacier is moving. The ice in the glacier is moving from where it is accumulating, as in where snow, oops, sorry, I need to move my thing out of the way, but it's moving from where the snow is piling up and forming into ice in excess and heading down to where it is ablating, or where the glacier experiences a net loss of mass because melting, calving, and sublimation outweighs snowfall. And the ice mass balance is a value. It's the value representing the balance between accumulation and ablation of snow. And it'll be a positive number in the zone of accumulation and a negative number in the zone of ablation. If the ice mass balance is 0, we are at the point of equilibrium. And indeed, on a glacier, scientists can define something called a line of equilibrium representing the line, and usually coinciding with the topographic line, since it's often dependent on altitude, between the zone of accumulation and the zone of ablation. And scientists will actually study this to see if the equilibrium lines appear to move. If they move downhill, that means that if they move downhill into the zone of ablation, then the glacier might be expanding. But if the equilibrium lines move uphill into the zone of accumulation, it's a sign that the glacier is retreating. And here's a visual display of equilibrium lines. You can see that we have two glaciers in this figure that feed into each other to become a single glacier, kind of like how two rivers feed into one another to become a bigger river. And notice how snow and neve, which is kind of granular snow, are forming above the equilibrium line. They are forming a layer on top of the glacier ice, and they actually compact over time to form more glacier ice. And that's where the glaciers are accumulating. The two glaciers each have equilibrium lines corresponding to the altitude above which snowfall is overall causing the glaciers to grow. And you can see the equilibrium lines for the two glaciers are about in the same zone because it is really dependent on altitude much of the time. It's going to be dependent on above a certain altitude, you're going to have enough snowfall that the glacier is accumulating. Below it, there's going to be less snowfall than there is loss to sublimation and melting. And as the glaciers merge and move downhill, there's going to be not as much snowfall, and the glacier is going to get smaller and weaker until at a point it's going to break up and melt before it moves any farther. I've been lucky enough to see the foot of a glacier in Argentina, and it's kind of like an ice wall, kind of like how I described in the edges of icebergs. The ice just kind of melts there and falls off in chunks. Now notice how there's notice how there's a number of ridges at the end of the glacier and how there's more than one. Those ridges are known as terminal moraines, and the ridge right at the toes of the glacier is the present terminal moraine. It's where the glacier ends presently, and it's where all the sediment being shoved by that glacier is ending up. You notice there's a couple that are further out, further downhill, and those formed when the glacier was at a greater extent, actually. This farthest one represents the farthest that this glacier has extended recently. And so there's evidence, thus, that this glacier is retreating. There's a present terminal moraine that marks the current end of the glacier, and then there's a couple of other remnant terminal moraines further downhill. So that's something we'll come back to, and it's a concept you'll also come back to when you do a lab on glaciers next week. So a glacier like the one in the previous diagram can actually move in one of two ways. Now, you might think that since a glacier is made of solid ice, it's going to slide downhill like a block, like in the picture on the lower left. And glaciers do actually move like that some of the time, but that's actually less common in Antarctica for the very reasons I described earlier. And that has to do with little meltwater because it's a cold-based glacier, and thus very little lubrication. Glaciers overall, and especially those in Antarctica, move by what's called plastic flow. The ice being pulled downhill by the force of gravity reshapes itself, rearranges itself, and actually flows like an extremely slow, thick, viscous fluid. And the ice doesn't really break up. And a lot of this involves the crystals changing shape very slowly. The glacier is normally under continuous, relatively low-scale stress from just the force of gravity bringing it down, and the ice can slowly change shape and rearrange under that. Now, basal sliding is when the glacier just moves as a discrete piece, and basal sliding needs lubrication to occur. And it tends to occur in kind of a stop-and-go fashion since the lubrication comes from meltwater that may not be a constant presence. And basal sliding is going to happen much more in the summer than in the winter because there's more meltwater. And it's also going to happen much more frequently and much more continuously in temperate glaciers or warm-based glaciers that have more meltwater overall. Now, a single glacier is going to be experiencing a combination of basal sliding and plastic flow in different areas. The basal sliding is actually going to often occur where the pressure is highest, because where the pressure is highest, that causes more water to melt, and that allows more meltwater to build up and help lubricate. And where the pressure is less, kind of like in the front of this example here, it's going to be dominated by plastic flow because there's not as much meltwater. And one thing I want to draw your attention to, and I do apologize, I didn't mean to have my face over this for a bunch of this lecture, but in this diagram here, this compares movement in the ice. they track how the ice, so they basically track, they basically pick like a vertical line, like they take all the ice on this vertical line, and they see how the ice at those different points in depth in the glacier end up moving over the course of 10 days. So in a polar glacier, which has very little basal slip, it has very little in the way of the glacier just moving as one piece, and it ends up being more dominated by deformation. You can see that the line has really just, it looks like it's been really just kind of pulled like taffy over to the right. It looks like the whole starting line has been warped in the direction of glacier movement. The glacier is moving that way, and it's been warped quite a bit in that direction. Now, with a temperate glacier, you can see that there is some warping still. It's not a straight line, but you can see that it's more straight up. It looks like part of the time it's kind of been just shoved over to the side without being warped, and it has been warped, but the warping and plastic deformation dominates it much less heavily. So temperate glaciers slide down more because there's more meltwater, and that's much less common in Antarctic glaciers because Antarctic glaciers don't produce a lot of meltwater, it turns out. Antarctic glaciers are dominated by plastic flow. And the important thing to understand about ice is that ice, when subjected to constant pressure or to relatively low pressure, or stress, excuse me, when it's under relatively continuous stress or low levels of stress, it will warp in response. Stress causes things to warp or to break, and not to anthropomorphize, but generally objects will want to deform as much as possible, and then they'll break. And ice is quite good at deforming without breaking, actually, if it's not being put under a ridiculous amount of pressure. When it's put under a lot of pressure, when it's put under a lot of stress, it forms crevasses. But when the ice in glaciers is just flowing gently around curves, when it's flowing over relatively even terrain, the ice just kind of shears and deforms, and the crystals rotate in different directions. The crystals slide past each other. The actual atomic structure of the actual crystal lattice itself, the way that the water molecules are arranged changes. And it's kind of plastic. It's kind of like what happens with the asthenosphere. Remember, the asthenosphere is the sort of solid but plasticky layer of Earth that the plates, the rigid lithospheric plates, kind of float over. And so the diagram on the lower left gives you an example of one possible process. You have an ice crystal that kind of gets sheared over in this direction, and it's kind of like what happens with Ekman transport, actually. The top layer gets deformed and it kind of drags, the top part of the crystal gets dragged in this direction, and it drags the crystal underneath it, but not quite as strongly because of friction, and so on and so forth, down to the bottom. And you get this dislocation occurring along these planes in the direction of glacial movement. And it turns out that when glaciers stop doing this, when the ice in glaciers goes from being able to deform and rearrange to simply breaking in half, that's when you get sort of a relatively sudden disturbance by glacial standards. And something that can be a bit confusing is that some of the disturbances I'll describe might not seem like they come across all that suddenly, but glaciers move really slowly, and so they can be heavily affected by, say, a bump underneath them, or an especially sharp turn. Because it turns out bumps underneath the glaciers, or especially sharp turns, are actually what causes what's known as brittle failure. And brittle failure is a nice way of saying the ice breaks. Brittle failure means that the ice crystals, instead of rearranging or shifting around, instead tear apart from one another under a large or a sudden force. And one example is when the underlying topography, whatever ground the glacier is flowing over, becomes rougher. Like you have a rock type that is harder and more resistant to erosion, or you have a bump, or you have a combination of that, because those bumps, it turns out, are often outcrops of rocks that resist erosion more heavily. And the disturbance caused by the presence of a boulder, a mound, or a resistant rock causes the ice to slow down when compared to the ice around it. And remember that glaciers don't flow at the same rate. The interior of the glacier is usually going to flow faster because it's less subject to friction. But in general, you want to think about how if part of the glacier starts flowing at a different rate from another part really rapidly, that's what can cause crevasses. That's what can cause, or relatively speaking, as far as a glacier goes, but that's what can cause crevasses. The disturbance caused by the presence of a boulder, a mound, causes the ice to slow down, and plastic deformation doesn't fix the disturbance because it happens too quickly for that to happen, and so a crack forms in the ice. And that crack is known as a crevasse, and many of them are quite large and deep. They're very dangerous, and those who venture into the interior of Antarctica have to undergo mandatory crevasse safety training and simulated crevasse rescue before venturing out near them. One thing is that it can be unpredictable as to when they're going to show up. They can form and disappear seasonally because different amounts of meltwater can occur seasonally, and that can cause the glaciers to flow with more difficulty or with less difficulty. They can form as the rock underneath them. They can form or disappear as the rock underneath them changes shape as the glacier goes over them. They can also form when a glacier is forced to make a relatively sharp turn, as we'll see on the next slide. But in general, they can be kind of thought of as a blister of sorts. They form when the ice is unhappy in the sense that its flow has been interrupted by something underneath it or by a sharp turn. And here you have a really nice example of a bunch of crevasses really looking kind of like blisters on a sore. I hate to make that gross comparison. And below you have an example of how crevasses can form around a really sharp turn. So in the left picture, it's happening where the glacier is flowing over a mound, and that's causing a relatively sudden disturbance by glacier standards. And on the right, the glacier is coming around a sharp turn, and the part of the ice on the inside is experiencing a relatively intense and sudden stress from this, and it starts to undergo brittle failure. Now, so this is the inside of the turn here. On the outside of the turn, kind of in the foreground, where the ice doesn't have to change direction as quickly, it can still mostly continue to move via plastic deformation. The ice can rearrange itself. And it really is kind of a question of how, relative to the glacial flow, how sudden it is. It's kind of like a river put down in slow motion, because if this was a river, think about it, the flow of the water would be, you'd have splashing and have rapids in areas where there's rocks underneath or where the water's being forced around a sharp turn. And that's kind of happening to a slow degree here, except it's causing cracks in the ice to form rather than rapids in the water to form. And just as you don't really want to jump into rapids without knowing what the hell you're doing, you also don't want to be messing around near crevasses because you could fall into the deep cracks and end up trapped down there. So movement within a single glacier is going to be quite complicated overall, and it's going to depend on factors like the strength and type of the underlying and surrounding bedrock, the shape of the surrounding topography, where the equilibrium lines are, and what sort of turns a glacier makes on its route. Glaciers can move as a concrete piece and undergo basal slip when meltwater at the base lubricates them enough for this to happen, and this is going to occur in the highest pressure areas. Since high pressure creates more liquid water, that's going to be less dominant in the polar regions like Antarctica. Glaciers, especially those in the polar regions, largely move via plastic flow, in which the ice changes shape and deforms without breaking. And then you get crevasses forming when glaciers undergo sudden disturbances. Flowing over hard rock or mounds or around corners will cause different parts of the ice to flow at different rates and create a sudden stressor and cause brittle failure. And during the second half of the lecture, one example of glacial erosion we'll talk about is an interesting example that happens when glaciers exit the stage of flowing over a mound of more resistant rock and when the pressure drops again, and that is plucking. So lecture 11B, lecture 11B, sorry, my mouse is really not behaving tonight. Lecture 11B is all about what do glaciers do to the rock around them as they move, because they break the rocks into tiny pieces, and we'll learn about what the record of glacial erosion looks like, what that can look like in the rock record, what that can tell us about past climates. And we'll talk a little bit also about how glaciers can be used to study climate change, which is a topic we'll return to much more heavily in a couple of weeks. So lecture 11B coming up next.